Hello, welcome to another Teardown Tuesday or Tuesday Teardown. I kind of like Tuesday Teardown. I'm ignoring. Anyway, welcome. Where's that chat? So, this is our third Teardown Tuesday, and this is really exciting because today we're looking at one of our own products. Previous couple of weeks, we've looked at a Strymon conduit, a Morningstar relay interface, and taken a look at what's going on behind the scenes with those. But today we're going to be kind of like a bit of a deeper dive into our new MIDI Thru Gizmo. So we'll be doing more of a, showing off all the functionality and connections and things like that in another stream, maybe on the weekend. But this is aimed at what is it and how does it work and how did we design this? And hopefully this is really interesting if you want to, or you're interested in making your own kind of digital electronics. It's not too complicated. So hopefully we can show you what's going on under the hood. And this is fully open source. So all of the design documents, the schematic, the PCB files, mechanical drawings, things like that will all be available. It's going to come in this. You've got a really nice, let me go to the overhead here. It's a little framey. Sorry about that. Hopefully you can see it okay. It looks a lot better in person, but this really beautiful like black and gold PCB. And then there's the top. So we'll be exploring how this works. But first of all, let me explain why we wanted to make this. So we'll probably cover this in another video, but behind me is our new PCB assembly equipment and electronics manufacturing line. And that allows us to take a bare PCB like this from the PCB manufacturer and go through all of the steps required to place the components, place the solder, and process that board so it is a fully functional circuit board ready to go into our products, which is really exciting. But that kind of machinery, does have a bit of a learning curve, and just requires you to make sure, make sure that your processes are really down and you've got a smooth workflow for that. Hey, Alec, how you doing, mate? Welcome. So we wanted not a starter project, but we wanted something where we could really get our feet wet and try our hand at this because the bridge boards for the Bridge 6 and Bridge 4 are a fair bit more complex in terms of the number of components, the layout and the design than something like this. This is a really great project for us to get started, but rather than just, a dummy test project, we thought, well, let's make something interesting and put it out there for everyone. So that's the idea behind this. And it's the first entry into what we're calling our Gizmos. And Gizmos are going to be a line of open source, fun products that you can either purchase from us, pretty much wholly assembled. Don't mind the printer. Or you can, take it and modify it to create your own version. You can do all that because it's all going to be open source and freely available for you guys. So that's really, really exciting. That printer is very loud, isn't it? So that's a bit of the why. That's my little boy coming in. Hey, Hugo. Oh, more paper. Anyway, sorry about that. He's great. So yeah, this is really exciting, and that's kind of the what. So we've got a whole new section on our website that we're putting up, and this is going to be hopefully really community driven and really just community focused. So if you guys have an idea for something cool that you want to have made, we'd love to kind of try and make it happen and make it available for everyone. So that's the idea. Let's take a look on the overhead. Actually, go to the overhead first. No, let's take a look here. So this is the for these open source projects, I'm doing the design, both the mechanical and electrical design, in Fusion 360 for a few reasons. Eagle has been the mainstay of the hobbyist community for a long time now, and it's kind of reached the end. So if you're not aware, Eagle was bought by Autodesk 6, 7 years ago now, maybe more, don't quote me, a number of years ago. And they've basically taken Eagle and put it into their, design tool or suite, kind of the flagship product for that a lot of people know them for, Fusion 360, which does 3D modeling and design and CNC and 3D printer control and all sorts of stuff. And they've taken that to make it a bit of a one-size-fits-all product development environment, which has its pros and cons. But the reason that we've done it in this is because you can get free hobbyist licenses and education licenses, which is pretty cool. So, there's no prohibitive software for anyone to natively edit these files, but you can also just view them in Eagle or import them into other PCB software if you like. That's not a problem. Yeah, so it's a little bit of a mess. I've got a little bit of tidying up to do on the schematic, so don't judge too harshly. It's got a little bit of cleaning up that needs done before it's ready to go out to the world, but that's going to happen this week. There's an initial repository on GitHub already, and then we're going to be adding these PCB files up there. So let's just take a look at the schematic, and I'll kind of walk you through what's going on with that. And we can take a look at a side-by-side of the actual board and then the PCB layout and the 3D model and see what's what. All right. So I'll get those out of the way so it's a little more, how's that looking? Cool. So, hey, Elliot, thanks for joining. Will the MIDI in and through have any merge capabilities? No. So to do MIDI merge, you've got two options. You can do kind of just a dumb merge, which is basically where you logically tie the outputs of various, kind of inputs and things like that together. And you hope that signals don't arrive at the same time, because if they do, they're going to get garbled and interfere with each other, and they're going to just give you garbage output that's not usable. You can do it if you're only sending some CC or PC messages every now and again, maybe. But the proper way to do it is in, some form of dedicated, chip to handle that, typically a microcontroller. So, for example, on a bridge, the main microcontroller handles all the different MIDI inputs, filters them, and then sends them out to various outputs as dictated by the user. So there's no microcontroller on board of this design. It is designed, the aim of it is that you want to send your MIDI to lots of places. So there's one input, and then you can send it to a whole bunch of outputs and configure how what TRS mode it's in. And that's the primary goal of this. I should have done an overview to start with. Sorry. So let's just switch to the top-down camera if we can. And I'll show you some stuff. I really should have started with this. Sorry, guys. This is the board. We'll take a look at the schematic in a bit. But we've got here one MIDI input. We have a MIDI through port. Now, they are both type A. So type A, type B, you can flip around with just switching the tip and the ring in a connector. So I'm going to talk about the different MIDI TRS types in this stream as well. We'll get to that a little bit later. But MIDI type A, which is the same MIDI type we use on our bridge products as well. So you've got that, and it's going to come with a nice laser etched acrylic case with markings for all the ports. It's going to be really nice. Then we've got 1, 2, 3, 4, 5, 6, 7, 8 outputs. And they are all, and you see there's 8 of these, they're called dip switches, but they're just little kind of, on or off selectable switches. And that's where you can adjust the output type, the TRS MIDI type, for every output independently. So let's say you've got something like I've got a space race here. This uses a different type of MIDI. It's not type A or type B. It is tip active, which means it just sends a voltage signal on the tip, and that's incompatible with somewhat incompatible. You can do it with a separate cable, but it's a lot of special cables to make it happen for all the different types. It just is the voltage signal on the tip. Chase Bliss product is the same thing, but on the ring. Then you've got type A, you've got type B, then you've got things that are like splitters. And the inspiration for this came from there's the Disaster Area MIDI box. I'm not sure if you've seen that, but it's a similar idea in a bigger enclosure. It's only got 4 channels on it. But you can select from, I believe they do type A, then tip or ring or both active, depending on how you have it set. I don't think you can switch between type A and type B on that, which you can on this. So, horses for courses. But yeah, this is perfect for setups where you might have a bridge or another MIDI controller or, an interface from your computer, and you want to control everything from there. But, you don't want to have a really massive MIDI interface just to sort of split those ports. So you would have your MIDI input coming from, your bridge, your MIDI controller, whatever it is. And then all these output ports can go to all your different devices. You can use a cable to go to a DIN 5, TRS, 3.5mm, quarter inch, whatever it is that you want to do. And you can configure exactly what type of, the port is without having to use any special cables. So if you're just going to another TRS device, be it 3.5 or quarter inch, you just use a regular old cable and then you specify how it's configured using the dip switches. So it's pretty cool, pretty handy. We'll release pricing for this probably over the weekend. We just got to finalize a couple of things, but it's meant to be really affordable and accessible for people, probably like under $50 US. So perfect for slapping under a board and routing all your MIDI or on a desk in a studio. It's gonna be spot on. So that's the board. And we've got our 3.5mm jacks. We've got these dip switches. You can power it from either standard guitar pedal barrel jack, so 2.1mm center negative power supply, 9 volts DC. Then, it could do 12 volts DC as well. That's fine. You can also power it via USB. And this USB port's only for power, not data, but you can power it via USB, which is really handy if you're working at a desk in a studio. We've got some optocouplers, some logic circuitry there. Then there's an LED on board, which will flash when you receive messages. So we can take a look at that. I've got this plugged into a MIDI interface on my computer. So we've got our MIDI here. If you switch to the top-down camera there, we'll take a look at this. All right, hopefully you can see that all right. Now, provide power via a USB cable. And let's bring up Pocket MIDI. So I'm using this to send MIDI data to it. So we'll just send a control change. Oh, and you can see it's very brief, but that little flashing green light there, whenever we send that control change message, it's going to flash. If we go send a timing clock, we'll set it really slow. You can see it pulsing in time. So that's down at 5 beats per minute. It sends 24 pulses for every quarter note. So that translates to the speed of the LED blinking there that you can see. See if I can get it. Yeah, you can really see it there. So perfect for just diagnosing whether you're receiving MIDI messages correctly or not, what sort of traffic you're getting. So let's take a look at how it works. Like I said, this schematic is not very well tidied. It's there's signals everywhere. The labeling needs to be a bit better. It's in 2 sheets. This one's not too bad, but needs a bit of tidying, so go easy. But here we have our MIDI in. Now the MIDI in is the jack that I've got connected to the computer there. Oh yeah, Simon, you can bring that up. Is it able to be put in like the other corner at all? Yeah, nice. Cool. So MIDI in. That's the jack there. And that's this section here. We've got an optocoupler to provide full isolation as per the MIDI standard. So it will help prevent ground loops from your MIDI input coming into here. So this is our current loop. So when the ring, that's the ring and that's the tip. And so when the ring is providing your current source, and it can be either 5 volts or 3.3 volts, then the tip carries the signal and it's an active low signal. So when this drops to low, it's going to, you're going to get current passing through this LED, causing it to light up, which is going to give you an output here. And that's how the MIDI input stage works with an optocoupler. Then we've got these logic gates here, which is kind of funny looking if you're not familiar with it. And this is an inverting Schmitt trigger. Now, inverting means that it's going to invert your digital signal when the input is high, it will output low, and vice versa. And the Schmidt trigger, which we talked about in some of the previous Teardown Tuesdays, basically cleans up the edges of these because it's coming in through an optocoupler. Instead of being a really sharp, edge transition, which is really ideal for digital signals. Sorry, my hay fever's going through the roof, as it usually does. Let me get my glasses. So your Schmidt trigger cleans up those edges and gives it a really nice transition edge by it. How it works isn't really too important, but it has a logic threshold and helps provide a really nice clean signal. But it inverts our signal, which isn't ideal. So what we then do, we've got this MIDI through. So this just passes whatever signal comes in, signal goes out on the MIDI through. There's no kind of configuration of the type there. So the idea of that is if you want to, just link multiple of these devices together, you don't need to worry about setting the mode, things like that. So pretty useful to have there. But we invert it twice because it's a double negative. So it makes sure that the phase or the polarity of the signal is going to be correct on the output. Then we're using another one here to drive this LED, you can see. So we're inverting it again, and then we're using this LED in an active low configurations. So yeah, when that signal there goes low, you're going to get a voltage generated across the LED, which will allow current to flow. So that's sort of the input and the through stage. Now we've got some power filtering and selection here. So from our DC barrel jack, we've got a reverse polarity protection diode. It's a really not easy way of doing reverse polarity protection. It's a Schottky diode, which means it has a low forward voltage drop, so you're not losing too much voltage, but we're regulating down to 5 volts. So you can do much more sophisticated reverse polarity protections here, but you don't need to in this case because it's a very low power device. We don't care about that voltage drop. It's a cheap and cheerful way of doing that. It's going to work really well. Then there's just a simple Zener diode for some over voltage protection at 10 volts. It's sort of just a nominal value there at 10 volts. Like I said, there's nothing wrong with powering this from 12 volts apart from that diode. So whether that stays in or not, up in the air a little bit, but you don't really need too much protection around this when you're not driving, especially when you're not driving, sensitive audio circuitry and various regulators. The input voltage on the regulator we're using is quite high. It's actually, ignore that part number there. It's not a mic 5504-3.3. That's a 3.3 volt regulator from Microchip, I believe. It's the same footprint, but different part number. So we've just got some decoupling here with our 100 nanofarad capacitors, some stabilization on the output as per the application note recommendations for the voltage regulator that we're using. Then here we've got, you can see our USB port here. And when you're using, you can get USB Type-C connectors, which is what we use. And rather than having the 20 or 24, I can't remember how many it is, but pins required for full sort of Type-C, where you might have USB, 3 or 3.1 or what have you. It's like a USB 2 only port, and it makes it so much easier to solder, so much easier to inspect. You don't have pins underneath the connector and all sorts of nonsense. So you've just got the shield pins, 2 ground pins, 2 voltage pins. We're ignoring the data pins. We don't need those. And then we're just these kind of mode select pins. We're using a 5.1K resistor as per the MIDI specification to just make sure everything's going to be nice and kosher there. A little bit of filtering, some decoupling at that connector. Then we've got these 2 diodes tied together here, creating an OR function. That probably should be like moved over there to be a little nicer. A lot of this needs cleaning up, but we won't worry too much. What that does is this is a really common way of kind of selecting between 2 different power sources while making sure that you can't backfeed them. So an example, we could just tie these 2 lines together here without the diodes, and it would work fine as long as we didn't have both connected at the same time, because what would happen, let's say we have our DC power connected, and then we've also got a USB cable connected. Well, we get 5 volts here going onto the power pin, the V plus pin of our USB connector. But what if that's connected to a computer that isn't powered on? Well, you could destroy the USB port on that computer, or worse, if you're not careful. I've seen whole motherboards get taken out from that kind of back powering. So it helps protect against that. First and foremost, only it's going to block that voltage coming back the other way, and it will also prioritize. It basically prioritizes the higher voltage, because you're ORing these together. So whichever rail is just fractionally higher than the other, it's going to conduct across that diode and sort of going to preference that power supply. So it's a really nice method of having multiple power sources, because this is after our 5-volt regulator. They're both going to be at 5 volts there, so it's just whichever one's a little higher. Most likely, if you have both plugged in, it's going to be this 5-volt regulator output, because it's going to be like bang on 5 volts, ignoring any voltage drops. But the USB power, might fluctuate a little bit, might be 4.8 or 4.9 volts. So yeah, then just some more stabilizing capacitor after there, to help give us a nice kind of clean power supply. We don't need to do any crazy filtering here, because it's a very low power device. It's no sensitive components on there, I should say. Then here we've got the power pins for one is for our Schmidt trigger. Actually, we've got 2 of these Schmidt triggers, so they're just both there, and we've got 100 nanofarad decoupling capacitor there to make sure that they get a really nice ripple free power supply. All right, and as those components, those chips are switching, it's going to help absorb those transients there. So on the second sheet of our schematic, we've kind of just got some duplicated blocks. So we'll look at one of them. So this is how the mode select works. So coming from here, we've got this MIDI data invert, and that's just letting us know, this net here is going to be connected to all of these. And it's just a reminder that, this is inverted, so we need to deal with that. And each of these outputs has its own Schmidt trigger to make sure that you're not having any kind of loading issues, because this is providing a current loop for the MIDI signal. So we come out here. Now we can kind of start from this spot here, because this is where our MIDI signal is kind of, you've had that double inversion, it's cleaned up, it's ready to go. Now we've got these dip switches here. So there's 2 dip switches connected to the tip and 2 connected to the ring. So if you think about that as the entry to the socket, and the cable comes in that way, you can see that farthest one is the tip, and that one there's the ring of the cable. So on our tip, we don't want to have both of these connected at once. Okay, so the idea is this carries our data and this connects it to 5 volts. So we're deciding whether our tip is connected to 5 volts through this 220 ohm resistor, or whether it's connected to data. And if you were to connect both of those switches at the same time, you'd be kind of canceling out, shorting, not directly shorting, but through those resistors, connecting your data pin to power, which would just sort of be a null result. So we can do the same for our ring, and depending on how we have these configured, will determine what, where our signal is, where our power is, and so on and so forth. And the ground is always connected to the sleeve, because that provides the shield for the MIDI signal, or in the case of the tip or ring, it's the return path for that signal. So we've got some, again, this could be a little cleaner, but some indicators here. So how we select the different modes, so we can see for type A, this is how we want to have it set. So we'll use this one here. Hopefully you can see that pretty well. So type A, 1 needs to be off. So this is 1 here. All right. So 1, so you've got 1, 2, 3, 4 of these dip switches. So 1 needs to be off. So that is going to be open. Okay. So the ring is not going to be connected to our data. And in type A, we know that ring is our current source. And the tip is our signal. All right. Then 2 is on. So that switch is going to be closed, which is what we expect. That's going to provide the 5 volts through our 220 ohm resistor to the ring. It's good. 3 is also on, which makes sense because that's going to allow the signal, our data, to flow to be connected to the tip. That switch is going to be closed. And as you would expect, 4 is off because we don't want to connect the signal and our 5 volts together. And then for type B, it's just the opposite of that because we're swapping, the power and the data on those pins. Then for tip active, what we want to do is just have the signal on the tip and nothing on the ring. And then we have our ground sleeve connected. So you can see for tip active, they're all off except for 3, which is our signal going to the tip. Ring active, likewise, is all of them off except for 1, which is our signal going to the ring. And tip ring active is where you might want to use a Y splitter to send, essentially kind of split that MIDI to 2 different devices, which isn't normally advisable for, your type A or type B MIDI types because it is a current loop. It's usually not going to work very well, but when you're using just the tip or ring active, which is a voltage, it's confusing wording, kind of weird nomenclature, but it is what it is. So the tip and ring active is just like a voltage signal, whereas the type A and type B uses a current loop there. So for the tip and ring active, you can kind of get away with that. You might have maybe some ground loop issues if you're not careful, and depending what you're connected into, but you can certainly kind of Y split that, and as any reasonably high impedance input isn't going to load those down too much. So for that, we just connect both the tip and the ring to our data, and away we go. And that's it. Like I said, it's not very complex in terms of how the circuitry is put together. I think it's pretty straightforward. Hopefully that's a reasonable explanation of what's going on. And now we can see the PCB layout here. This is a bit of an interesting case in how I would do a PCB layout, because I knew that on the back, I wanted to have this. We'll look at our bottom layer primarily. I wanted to be able to have, I'll show you a blank board if you can see the top-down camera, this kind of nice like artwork with a gold finish. And I wanted that to look uninterrupted. So I didn't want to have traces running all the way across it and heaps of vias. And in order to get that gold, so that's an ENIG finish, which is purely decorative here. You don't need that. The advantages of an ENIG finish is that you get a flatter surface versus hassle, like hot air solder leveling. So it's really good for like BGAs or high pitch, QFNs, things like that. But it's purely aesthetic here. But I wanted it to be nice and uninterrupted. And so that, you can see that there. That means that I didn't want to have any traces running on this back layer if possible. I've had to break that rule here and here. This PCB layout is actually a bit of a mess at the moment, so I'm not going to show you it too much because I was playing around with the jack placement to try and get the right coordinates set up for our pick and place, where I was sort of learning the ropes in there, and I just haven't sort of reset that. So if you see on the top, you can clearly see that I've moved the jacks around, and you've got these gross looking traces, and it looks awful. One, that would not work, but 2, that's disgusting. That's just because I've physically gone and moved this, up and it's not going to let me. Hang on, ignore violators. Up and down to try and work out exactly where I want that origin for the pick and place. So I'll fix that up before that gets pushed to the GitHub repo. But yeah, it's an interesting look into a PCB layout because I wanted it all on that top layer if possible. So there's a few liberties taken with the PCB layout, so to speak. Some rules of thumb that usually you want to try and obey and enforce, but this is such a low performance in terms of there's no high speed digital signaling going on comparatively, that you don't need to worry too much about how you're routing things, as long as you can get enough current to where you need it to go. Like the MIDI current loop uses single figure milliamps, so very low current demands. And then we've got our 3D model here, of course, which you can see everything going on there. So that's how it looks, kind of more brown than black on this render, but that's what's going on. That's our 3D model there. So let's take a look at it actually working and how we might configure the dip switches. Let's close that, I guess. I'm just going to open Pocket MIDI anyway. Here we go. I'll make that nice and big. Not that it needs to be. Anyway, that's good enough. Oh, hang on. The battery in my camera just died. 1 second. Bear with me, stream. Sorry about this. Really need to get an AC supply for this camera. Changing the battery is so finicky. Sorry about this, guys. Oh, I'm not even using my top front camera. I shouldn't have bothered. Oh, well. Why won't this battery come up? There we go. I'm going to try my best to have this fixed for the next stream, guys. Sorry about the hassle. We're getting there. We're getting there. Not pro streamers. I'm using my old 550D, my Canon SLR here as a webcam in OBS. So my battery just died, but hopefully, let me check OBS. Is that it doesn't like that? You know what? Whatever. That's fine. We're just top 10ing anyway. It is what it is. There we go. Sorry about that. Anyway. Pocket MIDI. Let's get rid of. Let's stop that clock. I didn't realize that was still running. So let's say Space Race by Alexander. Really nice pedal. Wow, it's monstrous. You can get an idea of how small this thing is compared to like a standard pedal. It's wee tiny. Let me grab some power for our Space Race. Bring this up a bit here so we can check out what's going on. So we'll have this plugged in here. Plug in our power. There we go. Lovely. Now, I'm going to use this port here, which is 1. Plug that in like so, and then I'm going from a 3.5mm cable to a 1/4 inch. So you can see if we plug this in here, now I've already configured this, I'm pretty sure I have, already configured this for this being the kind of utility jack as a MIDI input. Now, what we want, I believe, let me look up the disaster area, not disaster, sorry, the Alexander. Hang on, can I go into a, 1 second. What am I doing here? Let's get that off the screen. Guest mode. There we go. All right, Alexander Space Race. Let's just control the bypass. Oh, Space Race. I don't remember off the top of my head what the MIDI commands for that is. I could look up our device library, but this is going to be just as quick. There we go. Update procedure, blah, 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 blah. The manual. All right. Let's scroll down. Program change, bypass, presets, bypass. There we go. So it wants 102, which I think is what I was already on. Amazing. So 102 and 0 to 63 is going to bypass the pedal, and 64 to 127 is going to engage the pedal. So we can send, 64 is going to be fine. You can see when we send it, LED's lighting up, but it's obviously not doing the thing. because we haven't set the mode correctly. This requires a tip active MIDI configuration. So, like I said, we'll go back to our schematic here. And so for tip active, we want 1 to be off. So I can see that that's off. And we'll provide, with this, you'll get like a, on the enclosure or a little card, it'll have all of the, nice little diagrams for what to set to for different modes. So don't worry too much about that. But for tip active, we want 3 to be on, I believe. Pretty sure this is tip active. Anyway, we'll see. Now, let's see if that's going to play. Oh, it's already bypassed. We'll transmit that there. Let me clear that. So that should be. Let me check. I think you've got to make sure that the jack's in the MIDI mode so you can hold this down depending on the LED color. It'll red, which I believe is the MIDI mode that we want. I believe so. Just going to double check. Is this it doesn't say the MIDI type. Let's look up area MIDI box, because on the front it's got like a description. So Disaster Area and Alexander are kind of shared design there. So tip active Alexander. Okay. All right. So 3 is going to be on. Let me just check that out. All right. Everything's plugged in properly. So, hang on. We're in like the config mode. Power that off and on. There we go. So you can see that it's going to let me jump there. Yeah. So we're sending. I'll clear that so you can see the queue. So when we send it, it's going to auto transmit here, but greater than 64. If you can see on the top down there, the LED is turned on, so it's engaged. And then we jump back to there, and the LED is turned off. So you set it to the right MIDI mode, and you can control any any device you like, which is really cool. Like I said, I'm not going to go and set up 50 different TRS devices here. We'll try and do a stream showing something like that with a kind of crazy and wild implementation of as many ports as we can. But yeah, you can see that just how easy it is to get the right MIDI mode. That glare is kind of a thing, isn't it? I think that's a bit better. Just how easy it is to set, control different TRS devices. You've got 8 ports for that. So like I said, it's going to be open source. We're going to open that up for orders quite soon. I'd like this weekend or something like that. And we're going to be shipping those out. May. We've got all the parts ready to go for that. So we'll probably be doing manufacturing and shipping like the start of June, I'd say, or early June, where we've got all of our parts sort of ordered en route for our bridges. So our next round of bridges is a little behind schedule, but we're doing pretty well to be that only that much behind schedule. But they'll be shipping probably June. I wouldn't think any later than that because everything's inbound. No, shortages of any particular parts to hold us up. So yeah, that's our MIDI through Gizmo. I hope that was interesting in terms of a bit of the design process and how you might go about designing something like that for yourself, or just making some modifications to it if you wanted to. And I really look forward to seeing what you guys will do with this. So I think this is pretty potent in terms of what you can do. There's no need to mess around with like removable jumpers or anything like that. You can just configure the dip switches however you like, and yeah, send your MIDI everywhere. So thanks for tuning in for another Teardown Tuesday, unless I'll check with Simon if I've missed anything. Move the sorry Simon, you're asking me to move the Pocket MIDI window over and I didn't. All good. Thumb up from Simon. If you have any questions, shoot us a message, leave a comment, and we'll get back to you. Cheers, guys.